Everyone, this is Shantam Saxena, and I'll be presenting cloud benchmarking for maximizing performance of scientific applications. The paper was published in IEEE Transactions on Cloud Computing 2019, and the paper link is given in the first slide. So, to define the problem statement, the cloud computing marketplace has a lot of on-demand resources with a wide range of performance capabilities. This means that we have machines ranging from 4 GB RAM to 1000 GB RAMs, and this makes it challenging for us as researchers, as practitioners, to decide which compute resources will be usable and useful for us in terms of performance, cost, and performance and cost overheads. So this paper focuses on mostly on high performance computing applications, and the key performance indicator, which is called the maximum performance, is the minimum application executing time it takes. The authors here present a 6-step benchmarking methodology in order to determine the VMs that can maximize the performance of a scientific application hosted on cloud. Okay, in here a user essentially provides as input a set of weights that describes the memory, compute, communication, and storage requirements of an application, and then we go through the 6 steps of ranking a virtual machine with respect to all these criteria. So I'll be explaining one by one what these criteria are. First, step 1, we capture the attributes. The attributes of a VM that describe it are first selected based on experience with VMs and physical machines. So as an expert, as a domain expert, I take attributes of the VM which is application centric. For example, attributes such as number of integers and float and double addition, multiplication and division operations that can be performed in 1 second of a VM. So what is the frequency of computation required for me? Here these are actually the capture attributes, which ranges from 1 to n. Then we go for grouping the attributes. These attributes are now grouped into 4 categories: vis-a-vis, memory and process, local communication, computation, and storage. For example, attributes such as bandwidth of memory are read and write operations, and communication using pipes, etc., are grouped together as local communication group. And similarly, we have multiple groups in this when we group these attributes. Now we benchmark the virtual machines. Now benchmarking virtual machines is a standardized process where we use standardized benchmarking tools to run on our VPMs to capture this data. One of them which we use are Symlink and Bonnie++. Fourth step, we normalize the groups. Why do we normalize the groups? Because some VMs have their attributes based on their size of the VM capacity. So we normalize them so that the ranking is more standardized. Now we weight the groups. In the fifth process, weighing of groups happen because of domain expertise. For example, in financial applications, we don't need much of a storage requirement, but we need high IO. So there we give our weights. And the last one is rank VMs. From these 5 processes, we finally rank the VMs, and then we evaluate the scores of the virtual machines. For the critique section, this paper is able to capture the idea of importance and a methodology to actually benchmark the VMs of our cloud compute resources to the point it actually adds value to the practitioner before deciding the infrastructure of our project. Why this is important? Because when our project starts, we generally have all the budgeting and the resource allocation. We are able to add our own custom weights with domain expertise and experience. The literature and also the analysis enriches itself, and now from a quantitative perspective, we also have a qualitative attributes towards our calculations. The authors have also used 2 validation techniques. The first one is comparative, and the second one is enumerative, which actually enhances the perspective and analysis of the paper itself. The comparative method uses empirical analysis of the application, while the enumerative method uses the entire space of weights while making observations. Since the comparative validation cannot explain the distribution of rankings in the entire space of different sets of weights, the enumerative technique essentially has two rankings. One is the empirical rank, which comes from the comparative method, and second is the calculator rank, which we calculate in the using our weights. The distance between the empirical and calculated rank is computed as the sum of point-wise distances. For the scope of improvement, I only observed that only CPU-based VMs are used in the analysis, and I believe that with machine learning and deep learning applications gaining traction on the cloud marketplace, as we know, GPU level benchmarking could also be done at an application level, which can actually increase the scope of the problem statement altogether, and also can extend the scope when the VMs communicate with each other. That is when we have multiple containers interacting with each other, and how that bandwidth and latency happens there, and how it factors in between the speed of the application. And so also with this coming times, as researchers and practitioners, we need to be aware of our carbon footprint. So if we can have some compromise on the speed, but we gain in terms of reduced CO2 emissions from the compute resources, I think if we are able to capture that information on even on a qualitative basis, that could be very useful and very critical for a community of scientists and engineers. For the schematic diagram, as we discussed earlier, these are the 6-step process. The first, when we capture the attributes, then these attributes are grouped, then the VMs are benchmarked using those group attributes. We normalize those groups, we weigh in the expert opinions, and then we rank the virtual machines. I hope this